The beach where you played as a child is underwater by the time you're middle-aged. The river your parents used for drinking water tastes salty. The route you walked to reach neighboring villages now requires a boat you don't know how to build. This isn't a thought experiment. Between 14,600 and 14,000 years ago, humans watched their world redraw itself in real time. Sea levels rose 16 to 25 meters in less than 500 years, a meter every 25 years, 40 times faster than the rate we measure today. The question isn't whether humans survived. They did. The question is what it cost them. Glacial melt doesn't proceed at a steady drip. Ice sheets hold their mass for millennia, then release it in catastrophic surges when internal structure fails. Around 14,600 years ago, the Laurentide ice sheet, covering much of North America, began to collapse. The volume of meltwater entering the global ocean reached 2.9 times 10 to the power of 14 cubic meters. This injection didn't distribute itself gradually across centuries. It concentrated into a pulse lasting somewhere between 340 and 500 years, depending on which ice cores and coral records you prioritize. The rate matters more than the total. Sea level rose between 40 and 60 millimeters per year during the pulse's peak intensity. For comparison, current measurements sit around 3.4 millimeters annually. Meltwater Pulse 1A, the technical designation for this event, delivered ocean rise at nearly 20 times the pace that occupies contemporary climate discussions. A person born on a coastal plain would see the shoreline advance inland by over a meter by the time they reached adulthood. By old age, the beach of their youth would sit beneath several meters of water. This speed transforms adaptation from a cultural process into a crisis. Hunter-gatherer societies organize their subsistence around known resource locations, shellfish beds, river mouths, seasonal fishing grounds. These systems depend on stability across generations, where elders can teach younger members where to find food because the geography hasn't changed. When the shoreline moves inland at a meter per generation, that knowledge becomes obsolete. The places encoded in oral tradition simply cease to exist. The pulse wasn't uniform globally due to Earth's crustal response to shifting weight. When massive ice sheets melt, the land beneath them rebounds upward, a process called isostatic adjustment. Simultaneously, the ocean floor sinks slightly under the added water weight. This means some regions near the former ice sheets experience less relative sea level rise, or even temporary land emergence, while areas far from the ice, the tropical coastlines, the low-lying plains of Southeast Asia and Northern Europe, absorbed the full impact with no geological reprieve. The people living on those margins had nowhere to go but inland. The evidence for Meltwater Pulse 1A comes from organisms that couldn't keep up. Elkhorn coral, Acropora palmata, requires shallow water with sufficient sunlight for its symbiotic algae to photosynthesize. These corals grow upward at predictable rates, typically a few millimeters per year under optimal conditions. In cores extracted from reefs near Tahiti and Barbados, researchers found entire generations of these corals entombed in deep water, drowned in place. The coral tried to grow toward the light, but the ocean surface was rising faster than biological processes could match. Uranium-thorium dating of these coral skeletons provides precise timestamps for when they died. The dates cluster tightly around 14,300 years ago, with the drowning event lasting no more than a few centuries. The coral reefs essentially recorded their own death, preserving in calcium carbonate the moment when environmental change outpaced adaptation. These aren't isolated finds. Drowned reef sequences appear in tropical locations across the Pacific and Atlantic, all telling the same story of water rising faster than life could respond. Ocean sediment cores add a second line of evidence. Deep-sea drilling projects have extracted mud from the Sunda Shelf, the North Sea Basin, and the Gulf of Mexico. Within these cores, geochemists measure oxygen isotope ratios. Specifically, the ratio of oxygen 18 to oxygen 16 in fossilized plankton shells. Glacial ice is enriched in lighter oxygen 16, while seawater retains more heavy oxygen 18. When massive freshwater enters the ocean, the isotope ratio shifts measurably. The sediment layers dated to 14,600 to 14,000 years ago show exactly this signature. a sudden freshwater spike followed by gradual return to normal salinity as the pulse ended and ocean mixing resumed. The Antarctic ice sheet may have contributed additional meltwater, though debate continues about the timing and volume. Some models suggest a two-stage collapse, with the Laurentide releasing most of the northern hemisphere's contribution first, followed by Antarctic destabilization triggered by the initial sea level rise. Other reconstructions argue for near-simultaneous failure across both hemispheres. What's undisputed is the total, somewhere between 16 and 25 meters of global sea level rise, compressed into a period shorter than most modern nation-states have existed. The mechanism behind the collapse involves ice shelf dynamics. Ice sheets don't simply melt from surface warming. They collapse when their marine margins, the sections resting on ocean-submerged bedrock, lose structural integrity. Warm ocean water undercuts the ice from below, creating cavities that weaken the entire sheet. Once a critical threshold is crossed, the ice doesn't retreat gradually. It calves catastrophically, releasing icebergs and meltwater in quantities that overwhelm the ocean's ability to absorb the influx gradually. Look at a modern map of Southeast Asia, and you see an archipelago. Indonesia, Malaysia, the Philippines, thousands of islands separated by shallow seas. This fragmentation is recent. For most of the last 100,000 years, these weren't islands. They formed the exposed surface of a continental shelf called Sundaland, a landmass roughly twice the size of India, connecting mainland Asia to Borneo, Java, Sumatra, and beyond. Sundaland wasn't marginal habitat. Pollen cores and fossilized plant remains indicate a tropical savanna rainforest mosaic, rich in large mammals and positioned at the confluence of monsoon systems that brought reliable rainfall. This was prime real estate for hunter-gatherer populations. The region likely supported some of the highest population densities of the Late Pleistocene, serving as a corridor for human and animal migrations between Asia and Oceania. The archaeological record from this period is frustratingly sparse, but not because people weren't there. The oldest and most extensively occupied sites are now 50 to 120 meters underwater. What we can study are the highland refuges, caves in Borneo, coastal sites in Vietnam that were once far inland, places where populations concentrated after their lowland homelands flooded. These refuge sites show evidence of sudden population influx around 14,000 years ago, consistent with coastal groups being forced inland by rising water. Genetic studies of modern Southeast Asian populations reveal a massive dispersal event originating from this region during the early Holocene. Mitochondrial DNA haplogroups trace back to founder populations in Sundaland, then show rapid geographic spread across island Southeast Asia and into the Pacific. This pattern suggests not just gradual population expansion, but forced migration, groups fragmenting and moving because their original territory was shrinking beneath them. The flooding transformed the region's ecology entirely. A continuous landmass became an archipelago of isolated islands, separating populations that had previously interacted freely. For terrestrial megafauna like the Javan, rhinoceros, and banteng, this meant fragmentation of habitat into pockets too small to support viable populations. For humans, it meant the sudden necessity of maritime technology. Villages that had been a day's walk apart now required boats to reach. The development of sophisticated watercraft in this region likely wasn't a leisurely innovation. It was an adaptation forced by drowning geography. Sea level rise doesn't announce itself by flooding your home. It announces itself by poisoning your water supply, sometimes decades before the ocean becomes visible on your horizon. This process begins with saltwater intrusion, the invisible enemy that arrives ahead of the visible tide. Rivers and groundwater aquifers near coastlines maintain a delicate equilibrium between freshwater and saltwater. Freshwater, being less dense, sits atop the heavier saltwater in a formation hydrologists call a freshwater lens. As sea level rises, the salt water beneath pushes upward and inland. Wells that once drew fresh water begin pulling brackish water instead. Springs turn salty. The freshwater lens thins and retreats, and there's no amount of digging that helps because the salt is coming from below. For coastal populations dependent on these water sources, this means drought without a lack of rain. You can see the river, touch the water, but you can't drink it. Shellfish beds die next. Most freshwater and estuarine species, mussels, clams, certain crustaceans, tolerate only narrow salinity ranges. When the salt wedge moves upstream, these food sources collapse. Fish that spawn in river mouths, like salmon and sturgeon, lose their breeding grounds as the mixing zone shifts inland and the geometry of the estuary changes. The archaeological signature of this resource cascade appears in midden deposits, the trash heaps of ancient coastal settlements. Shell middens from Europe and North America show a shift in species composition around 14,000 years ago. The freshwater mussels and estuarine clams that dominate earlier layers give way to fully marine species, or, in some cases, the middens simply end. The sites were abandoned, not because the ocean flooded them directly, but because the food and water were already gone. Territorial compression follows resource loss. Hunter-gatherer groups require extensive territories to support their populations sustainably, typically several hundred square kilometers per band, depending on resource density. When coastal groups lose access to shoreline resources and are forced to move inland, they enter territories already occupied by other groups. The archaeological record from this period shows increased evidence of violent trauma on human skeletal remains, healed fractures from weapons, unhealed skull trauma, bodies in irregular burials rather than formal cemeteries. These are the physical traces of competition when the resource base shrinks too quickly for populations to disperse peacefully. This cascade, salt intrusion, resource collapse, territorial compression, conflict, plays out before anyone's home gets wet. The crisis precedes the flood by enough time that populations have already destabilized by the time the water becomes the obvious problem. It's a slower violence than drowning, but more insidious because the cause isn't immediately visible. You know your well tastes wrong, you know the shellfish are dead, but the connection to sea level change isn't obvious when the ocean is still kilometers away. The North Sea is cold, deep, and has been a maritime highway for European trade for millennia. It's easy to forget it was once a plain. Doggerland, named after the Dogger Bank, a shallow area where fishing trawlers frequently snag underwater artifacts, was the heartland of Mesolithic Europe, not its periphery. During the last glacial maximum, when ice locked up enough water to drop global sea levels by 120 meters, the North Sea basin was exposed land, but Doggerland's peak habitability came later, during the warming period between 12,000 and 8,000 years ago, when the ice had retreated, but sea levels hadn't yet fully risen. This window gave Doggerland a temperate climate with vast grasslands, extensive river systems, and chains of freshwater lakes fed by glacial runoff from the retreating Scandinavian ice sheet. The fauna was spectacular. Mammoth populations persisted here longer than in most of Europe. Red deer, aurochs, wild horses, and roe deer grazed the plains in herds large enough to support substantial human populations. This was an empty steppe. It was a rich, biodiverse landscape that likely held higher human population densities than the surrounding highlands that we can actually excavate today. The archaeological evidence comes in directly. Fishing boats working the Dogger Bank and other shallow areas regularly dredge up Mesolithic artifacts, barbed bone points used for fishing, flint tools, harpoons carved from antler, and occasionally human remains. In 1931, a trawler pulled up a piece of worked antler, later identified as a harpoon point, still embedded in a fragment of auroch's skull. Radiocarbon dating placed it at roughly 11,000 years old. The Lehman and Ower banks, now submerged sandbanks, have yielded so many artifacts that archaeologists can reconstruct settlement patterns despite never conducting a formal excavation on dry land. Meltwater Pulse. 1A began Doggerland's transformation, but didn't complete it. The pulse raised sea levels enough to flood the lowest areas and turn the southern portions into salt marshes and tidal flats. The central region remained exposed as an archipelago of low islands separated by shallow channels. This phase probably lasted several thousand years, with human occupation persisting on the higher ground even as the landscape fragmented. The final submersion came later, around 8,200 years ago, possibly accelerated by the Storegga Slide, a massive underwater landslide off the coast of Norway that generated a tsunami. By 6,000 years ago, Doggerland had vanished entirely beneath the waves. Britain, which had been a peninsula of Europe, became an island. The populations that had lived on the plain either drowned, migrated to higher ground, or adapted to maritime life on the shrinking islands. The North Sea now sits where Europe's Mesolithic heartland once thrived. Every trawler net that snags on submerged peat, deposits, or drags up bone fragments is sampling a lost continent. The irony is methodological. Archaeologists study the highlands and caves where refugees fled, treating these marginal zones as if they were the centers of occupation, when in fact they were the fallback positions for populations displaced from richer lowlands we can no longer access. Climate systems don't respond linearly to forcing. They amplify through feedback mechanisms that accelerate change once a threshold is crossed. Meltwater Pulse triggered several of these amplifying loops, turning what could have been a centuries-long adjustment into a cascading reorganization. The albedo effect hit first. Ice and snow reflect roughly 80 to 90% of incoming solar radiation back into space, keeping the polar regions cool. Ocean water, by contrast, absorbs about 90% of solar energy, converting it to heat. As ice shelves collapsed and exposed dark ocean, the planet's energy budget shifted. More absorbed heat meant warmer water, which accelerated further ice melt, exposing more ocean, absorbing more heat. This loop doesn't have a natural break until the ice is gone. The flooding of tropical lowlands added a second amplifier. Sundaland's transformation from dry land to shallow sea created vast areas of coastal swamp and drowned vegetation. Organic matter decaying in oxygen-poor water releases methane, a greenhouse gas roughly 25 times more potent than carbon dioxide over a century-long timescale. Methane trapped in permafrost and shallow marine sediments also began releasing as temperatures rose, adding to atmospheric concentrations. Ocean circulation patterns shifted as massive freshwater pulses diluted the North Atlantic. The modern ocean's thermohaline circulation, the conveyor belt that moves warm water toward the poles and cold water toward the equator, depends on salinity differences to drive sinking. Freshwater disrupts this by making surface water less dense, reducing its tendency to sink. Paleoclimate records show the thermohaline circulation weakened or possibly shut down entirely during meltwater pulses, causing regional cooling in Europe even as global temperatures rose. This disruption had its own cascade effects on monsoon patterns, precipitation distribution, and storm intensity. The combination of these feedbacks meant the climate system wasn't responding proportionally to the initial forcing. Small changes in forcing produced large, non-linear responses. This is the signature of a system with positive feedbacks. Not positive as in good, but positive as in self-reinforcing. Once triggered, the system pushes itself toward a new equilibrium state rather than settling back to the old one. Modern observations of ice sheet behavior show eerily similar patterns. The Thwaites Glacier in West Antarctica, colloquially termed the Doomsday Glacier by media and some researchers, sits on bedrock below sea level. Warm ocean water is currently undercutting its marine terminus, thinning the ice from below in the same configuration that likely destabilized portions of the Antarctic ice sheet during Meltwater Pulse 1A. The glacier's grounding line, where ice transitions from resting on bedrock to floating as an ice shelf, has retreated several kilometers in recent decades. Computer models of ice sheet dynamics suggest that once retreat begins in this geometry, positive feedbacks make collapse difficult to stop. The ice sheet doesn't gradually thin. It breaks up catastrophically once internal stresses exceed structural limits. The feedback mechanisms operating during Meltwater Pulse 1A aren't ancient history in the sense of being irrelevant. They're demonstrations of how the climate system behaves under rapid forcing, and the physics hasn't changed. Ice sheets still respond to warm ocean water by undercutting and calving. Dark water still absorbs more heat than white ice. Methane still releases from thawing organic matter. The rates and magnitudes differ, but the mechanisms remain active. Australian Aboriginal oral traditions contain stories describing coastlines that have been underwater for more than 7,000 years. These aren't vague flood myths. They include specific geographical details, the locations of islands that no longer exist, the contours of bays that are now open ocean, the positions of freshwater springs now submerged beneath meters of seawater. Linguists and anthropologists working with indigenous communities along the Australian coast have documented dozens of these narratives. In some cases, researchers could correlate the described geography with bathymetric surveys, maps of the seafloor, and confirm that the oral traditions accurately describe landscapes that haven't been above water since the early Holocene. One tradition from the Spencer Gulf region describes when the sea came in and covered the land, flooding specific coastal features that bathymetric data shows were exposed until roughly 9,000 years ago. The precision of these traditions raises questions about the limits of oral transmission. How do you pass accurate geographical information through 300 or more generations? The answer seems to involve ritual formalization and redundancy. Many indigenous Australian cultures encode important information in song cycles, ceremonial narratives, and initiation rites, contexts where exactness is enforced through repetition and social consequences for error. The information isn't just passed casually from parent to child. It's embedded in the cultural structures that define community identity. The emotional content of these traditions is equally striking. They don't describe the rising sea as a distant event. The language conveys trauma, the loss of homeland, the separation of communities, the necessity of relocating to unfamiliar territory. This suggests the flooding wasn't experienced as a gradual, generation-by-generation adjustment, but as a crisis rapid enough to create lasting psychological impact. Other cultures have flood traditions that may encode similar events, though dating them is more speculative. The Mesopotamian flood narratives, preserved in the Epic of Gilgamesh and later adapted into biblical tradition, describe a world-altering deluge that resets civilization. The Gun-Yu flood myths of ancient China describe catastrophic flooding requiring massive engineering works to control. The Manu flood narrative in Hindu tradition describes rising waters that submerge the known world. Attributing all flood myths to Meltwater Pulse, 1A would be overreach. Floods occur frequently from various causes: rivers, storms, tsunamis, and humans have always lived near water, making flood experiences common enough to generate mythological traditions independently. But the timing is suggestive. The period between 15,000 and 8,000 years ago saw multiple meltwater pulses, not just the dramatic MWP-1A. Populations living on any coastline during this span would have experienced rising seas within living memory, and the catastrophic pulses would have been impossible to ignore. The witness problem is that we can't interview the people who lived through Meltwater Pulse 1A directly. The stories that survive did so by being important enough to preserve through immense spans of time, which means they were filtered, formalized, and adapted to serve cultural functions beyond simple historical record. But the core geographical accuracy in some Aboriginal traditions suggests that at least some details of the original experience survived intact, encoded in narrative form, and transmitted with enough fidelity that modern science can verify them thousands of years later. Humans didn't go extinct during Meltwater Pulse 1A. Populations migrated, adapted subsistence strategies, developed new technologies, and occupied previously marginal territories as their homelands submerged. In biological terms, Homo sapiens weathered the pulse successfully, but biological survival and cultural continuity are different metrics. The civilizations on the coastal plains, their territorial knowledge, resource maps, burial grounds, and sacred sites didn't survive. People abandoned not just physical locations, but the framework that defined their world. Imagine leaving a landscape your ancestors occupied for 500 generations, where every hill and spring held a story. The refuges where displaced groups concentrated were foreign, often already occupied, requiring negotiation or conflict. Technological shifts highlight this cost. Maritime technology in Southeast Asia and the Pacific likely advanced rapidly, driven by the need to maintain contact between communities separated by rising seas. But these innovations came at the price of older systems becoming obsolete. Walking routes, seasonal camps, and hunting grounds that shaped life for millennia vanished under new coastlines. Genetic bottlenecks in modern populations also reflect this disruption. Several regions show evidence of severe contractions during the early Holocene, consistent with land loss forcing groups into smaller, isolated pockets. Genetic diversity drops when populations fragment, and the alleles lost in a bottleneck never return. The lesson isn't that catastrophe is unsurvivable. Humans are adaptable and capable of radical shifts when forced. The lesson is that survival and continuity are separate outcomes. You can save the species while losing the civilization. Adaptation costs not only lives, but worlds erased, territories, knowledge systems, and identities tied to landscapes that disappeared. Coastlines redrawn within lifetimes forced populations to choose between migration and catastrophic loss. They chose survival, but what they built drowned. The post-pulse world was not a continuation, but a reset. The physics behind the pulse remain active. Ice still rests on bedrock below sea level. warm water still undercuts marine margins. Positive feedback still turns small changes into cascading reorganizations. The rules haven't changed, only the current state of the ice. Adaptation is possible. Humans proved that 14,000 years ago, but it costs everything built in the world left behind.